The next talk is by Jezabel Curbelo from the Polytechnic University of Catalonia here in Barcelona. The title will be about the exceptional Arctic stratospheric polar vortex event.
Thanks, Emilio, for the presentation, and thanks, Salvador, for the opportunity to give this talk. I am going to talk about an Lagrangian tool to analyze the exceptional Arctic stratospheric polar vortex in 2019-2020. This is a joint work with Gan Chen and Carlos Roberto Mechoso from UCLA. As you probably know, the polar vortex is a strong band of wind in the stratosphere around the pole, and it is about 15 and 45 kilometers above the surface. And this strong band, when it's very strong, prevents horizontal mixing and also contain or enclose cold air in their interior. But have Ileana told before, in some moment this polar jet weakened and could be displaced or split in two, and the jet stream is wavy. So with that idea, we want to study the Northern Hemisphere stratospheric winter during 2020. And this event was very important because it was the strongest, more persistent and coldest in record in the Arctic, and also the ozone depletion in that period was very strong and was record. So we focus in this event from a dynamical point of view. We want to study the transport and mixing problem and the flow structure that lead the split, and how the transfer fluid particle move to one vortex to other during the split. Because during spring 2020, this strong polar vortex split in two, and the ozone poor air also split with the polar jet. So we go to follow a Lagrangian points of view. We go to use Lagrangian tool, and that means we are going to follow parcel trajectory. Even we study transport, the study of transport in a flow that are control. Also, the study transport is a difficult task because the parcel trajectories could follow very intricate paths as the one that we see in the first panel. So we need to looking for some guide to select parcel trajectory that behave similarly. So we need to looking for some structure that guide the selection of our initial condition to classify the different paths or the different transport routes in our system. So this structure in a dynamical system community are called Lagrangian coherent structure. Lagrangian because are based in trajectory, is followed parcel trajectory, and coherent because they leave tiny lobes to significantly affect the transport. This definition was introduced by Haller and Joan, and the Lagrangian coherent structure are defined as a transport barrier and show the strongest attraction, repulsion, or sharing in the flow. So localize the Lagrangian coherent structure help us to identify regions with parcels have similar dynamics, similar dynamical fate or origin, and similar behavior. There are several tools to detect or compute Lagrangian coherent structure. The most popular are the finite time Lyapunov exponent. And I go to present here another one that is called the Lagrangian descriptor. We have proposed this tool that is based on compute the length of the parcel trajectory. That means we define the function m as the arc length or Euclidean arc length of the parcel trajectory that start at x0 forward and backward in time. That means for each point of our domain, we at time 0, we take the forward trajectory and the backward trajectory in some interval of time given by tau. So we take the length of this trajectory, and at the length of this trajectory, we have a number, and this number is the value of the M function. For instance, we see in that picture, we start in that point, we take the forward trajectory and the backward trajectory, and the corresponding number is the value of the M function. The M function on the Lagrangian descriptor depends of the value of the interval, of the length of the interval. If the length is short, the figure that we obtain is we repeat this person in all the points of the domain is very smooth, but if the interval is long enough, we could highlight some feature that singular feature highlight the stable and unstable manifold and the coherent structure of the flow. So thanks to that tool, we could detect and localize this Lagrangian coherent structure. For instance, so this is very important for my work, the detection of hyperbolic trajectory. The hyperbolic trajectory are the intersection of stable and unstable manifold. And we see here the result is we applied the Lagrangian descriptor. And why these structures are important in my work? Because when we localize this type of structure, we know the behavior of the parcel around it. We know that the parcel approaches the hyperbolic trajectory following the stable manifold and move away following the unstable manifold in red. So this type of structure helps us to describe and characterize the transport in a neighborhood. Regarding to the data, I use ERA 5. And I focus in the velocity field, in particular in the horizontal wind velocity. And in this study, I also use the ozone. So before to explain our result, I need two ideas. So the first idea is a definition of the kinematic stratospheric polar vortex, because I need to say what particles are inside and what particles are outside our polar vortex. So there are definition of the classical definition of the polar vortex is given by the maximum of the potential vorticity gradient, taking equivalent latitude. But in our case, as we are compute the Lagrangian descriptor for every day, so we need we propose a definition based in the Lagrangian descriptor. This definition is justified or using the ergodic theory. So the idea of this definition is we have a Lagrangian descriptor as we see in the picture. Dark blue correspond to short trajectories. Yellow correspond to long trajectories. Remember that the M function gives us the length of the parcel trajectory. So we have shown that the large value of the M contour set act as a transport barrier that prevent the are invariant set and act as a transport barrier. So this contour set divide the core for its surrounding and also are free to hyperbolic trajectory. We don't interested in the hyperbolic trajectory in this type of definition because hyperbolic trajectory produce filament. So we need a barrier that divide without filament processes. Between all the possible values that we plot in the probability density function, we take the limit of the failed tile of the M value as the definition of our kinematic boundary. The reason is experimentally, numerically, that type of this value work very well for our problem. So in the figure, we see that the proposed boundary is the red line. The black line is the classical definition using the potential vorticity gradient, and the blue line corresponds to the maximum of M value for each longitude. We go to use the blue line to divide the parcels that are in the outer part of the vortex and in the inner part of the vortex boundary. So with this definition, we could have this type of figure. Here we use an example of September 22 in the southern hemisphere. So if we evolve this type of boundary, we observe the behavior of the parcel for this event that have a split event in the southern hemisphere. And here we see the comparison with the Lagrangian descriptor tool. We see that the Lagrange, if we take the gradient of that figure, we see the lines, and the line highlight the stable and unstable manifold of the flow. So this manifold go to get the transport as we go to see now. So if we have a parcel in that area, that is the parcel A, we know that the parcel move until the hyperbolic trajectory following the stable manifold and moves away following the unstable manifold. So it continues rotated in that vortex in the western hemisphere. If we have a parcel in B that is there, also approach the hyperbolic trajectory following the stable manifold, move away following the stable manifold, and continue rotated in that part. And if we have another parcel C that is in the outer part, so this parcel moves to one vortex to the other, as we see in the figure. So at the end, we have a vortex that continues rotated in this area, and we have a vortex that continues rotated in this area. So this structure gives us a criterion, the relativity position of the stable and unstable manifold gives us a criterion that in a future time the vortex go to split or not. With these two ideas, we start to study the Northern Hemisphere winter in 2020. The first thing that we take, well, we know that this vortex is split at the mid-end of April. So we start in the 10th of April. We plot here the Lagrangian descriptor. We highlight the hyperbolic trajectory. We compare this value with the ozone in the region. So we see ozone pure air inside the vortex and largest value outside, and the black line highlight the singular feature of the first panel are highlighted in that panel in red. And it's particularly interesting, this hyperbolic trajectory. This hyperbolic trajectory, yes, because if we see the ozone in that part is stronger and follow this hyperbolic, this manifold. So we see the signature of the manifold in the ozone. the other tool that we could use is the definition of the vortex boundary that I have already explained. So we divided the polar vortex into color in the exterior part and the interior part of the vortex, and we go to study the evolution of that parcel. If we continue with the evolution, we start 10th of April, and we see that the vortex wave, and in some moment we have a pinching structure of the manifold and intersection of the two manifolds, and we see the same toy of the parcel that we had before. So we now could apply our criterion for vortex split. So if we highlight the relative position of the stable and unstable manifold, we see if I have this type of structure, that means parcels that are inside move, are outside, move inside, following the stable manifold and continue rotated in that area. So one vortex is formed in that hemisphere and the other vortex is formed in that hemisphere. But if we found that the structure of the manifold are in that way or in this other position, we only have one vortex in a future day. For that case, we are in the first case, so the position of the stable and unstable manifold are in that way, so the vortex is split. So now I go to continue with this idea, but added the ozone parcel of a tracer. So we label it in that case. In the figure, we see again the singular feature of the Lagrangian descriptor in black, highlighted, taking the gradient of that function. The outer and inner part of the vortex boundary in red and in blue, and also we have the parcel of ozone. We divided the ozone, well, we consider that the ozone that are inside of the vortex is the ozone that is the 10% lower in the high level. So for this parcel, we differentiated two times. One for the ozone that are lower to the one for the ozone that are between 2% and 10%, and the blue for the lowest 2% of the level. So with this type of picture, we study now the evolution, and the first thing that we note that is around the 15th of April, a singular feature appear between the two levels of ozone, that the feature appear there, as we see a black line there. And this black line is so important because continue in the evolution and divide the vortex in two. And this manifold is very important because when we arrive to the pinching event and the split event, this manifold divide the parcel with larger ozone value with the parcel with lower ozone value. So all the parcel with lower ozone value continue in the main vortex, and the other type of parcel are in the split vortex that are moved in the Western Hemisphere. This result has been published in Geophysical Research Letter, as has appeared as a cover of the issue. We also study what happened after the split event. And we have seen that the main vortex are present in the stratosphere until mid of May. So here we compare the study using the deviation of the quasi-geostrophic strain function. So for the 22nd of April, we see here one of the vortex. This is one of the vortex, and that one is the other vortex. So the vortex over North America it tends to disappear in later time, but the vortex over Eurasia continue very stronger and deep in height until mid of May. So that is all in my work. So we have explored aspects of the evolution and transport in the lower and middle stratosphere. We have focused in the dynamical evolution and transport. We explained that a very important feature is the hyperbolic trajectory that appear near to the pole, because this type of structure control all the dynamic during the split and after. And we have also showed that the lowest level of ozone and concentrated all the time in the main vortices and split with the main vortices, and after that is displaced over Eurasia. And that's it. Thank you so much.
Thank you, Jezabel. So, questions or comments? I have one myself. I haven't. It seems that you can predict from the configuration of the manifolds the split or not split of the vortex. But I haven't understood the argument. Or is this is something empirical? You have a theory behind this? Or?
Well, yes, we have. It's true that I don't say predict because we are using analysis data. So it's true that I'm not predicting nothing. And the other thing is I am use forward trajectory, if we remember my definition. So here I need forward time to compute the forward trajectory. So this time of structure summarize the forward information that I have. This is two things. The other thing for this type of structure, that one is a very good question. For this type of structure, this shape of the stable and unstable manifold, in that paper, we compare this structure with a toy model, a toy kinematic model, and appear increasing and decreasing the waves 1 and 2. So we try to relate of this study with the Rossby waves, but we are far away of that one. And it's true that when we use forward trajectory, we could obtain the backward trajectory, sorry, we have the red position. So to try to predict, we need to know more about the blue manifold. For instance, if we want to predict, to compute this blue manifold, we could use forecast velocity. So the idea is, if we found this blue manifold using forecast velocity and we have the other manifold, the position of that manifold gives us some criterion of we have enough mass of air that come inside to split the vortex. So if there are a small space between one manifold or the other, there are not enough mass of air to divide the vortex. And that one is useful because the vortex split sometimes occur in some height and not in other, for instance.
More questions or comments? If not, yeah.
Is there a reason for which you observe the split between the region with poor ozone and rich ozone masses of air? Which is the physics behind, in the end, the split happens right at the boundary between the two masses?
Yeah, it's a good question, and I don't have the answer because I only use the ozone as a tracer. I don't explain more about the chemical processes or physics that are behind. I consider that from the dynamical points of view, I consider that the ozone is a tracer and moves with the velocity, and that's it.